Welcome, Mindsetters, to this Learn Extra Life session on a Saturday. Make sure you guys have your pens and pads out because we've got a full packed session just for you guys. By the way, so John, what are we going to be doing today?
Well, guys, it's paper 2.
All right, awesome.
Lots of chemistry. We did physics last week, and I know there are a lot of you that are still going to be writing paper 2 during this coming week. So get out your questions. Now, what are we going to do today? We're going to start with one of those previous exam question papers. We were all the way back to 2008, and we're going to be going through as many of those questions, different sections of the paper. We don't want to just get stuck on one topic because that's a bit boring.
No, definitely.
But at the same time, we're going to just be going over the key things you need to know in each of those sections.
All right, awesome.
So, but guys, if you've got problems, you've got questions, you want a further explanation, let us know on the page, phone us on the help desk number, and we'll get back to you. We'll try and answer all of those.
All right, so while John makes his way across there, I'm going to tell these guys what they need to do. Guys, make sure you get on the page. You know the link, www.facebook.com/learnextra. Get chatting to me, guys. If you're lost anywhere, as John said, make sure you post it on the page so I can get those questions to him so he can help you out. And guys, I am giving out these awesome winter packs. So make sure you call in on 0861 058 262. The first 5 callers to call in with the great question, you get to get one of these packs. But guys, make sure you keep chatting on the page though, so we can get those questions to John so he can help you out. And by the way, happy Youth Day, and I'm going to hand over to John now. John, take it away.
Thanks, Ty. Great to be with you, and let's get going. Now, remember in paper 2, a lot of questions that I've seen come up on the page already. What's in paper 2? You need to recognize we've got organic chemistry, and then we've got effect of reactions, chemical change. So we need to do rates of reaction, chemical equilibrium. And then there's electrochemistry, redox. And the last section is on chemical systems, which is batteries, fertilizers, chlor-alkali, all those industrial processes. We're going to jump in with one of the easy questions and the easy sections that it requires a little bit of book work and a quick summary of that. But I thought as a warm-up, let's get going with rates of reaction. So have a look here. We're going to be posting the question on the page as well. This is taken from the November 2008 exam paper, and I'll discuss what the trend has been in other exam papers so that you can get an idea of what's happening and make sure that you're absolutely ready and prepared for your coming June exam. Okay, so let's go to it. Rates of reaction. And remember what rates is about. What is a rate? A rate is what happens. It's the measurement of how much product is produced in a certain time. So what do we go to? In this question here, it says 8.1, the collision theory can be used to explain how different factors affect the rate of reaction. So we want to, of the chemical reaction, name 2 conditions. Now, when they put it in bold and capital, we need to make sure that we do give 2 that determine whether a collision between 2 molecules, A and B, will lead to a chemical reaction. So this is an interpretation of your theory, collision theory. Remember, we have reactant molecules. Those are the things that we have at the start. So collision, molecule A and molecule B. What turns them into a product molecule, an AB or an A2B or something like that? Well, first of all, the first thing we're going to need to say here is they need to have enough energy. They need to have enough energy. Right? The second thing that you need to recognize and you need to be able to say is they could have too much energy. They mustn't have too much energy, because think about it, we've got like particles rushing towards each other. They could bang into each other and spin off. We don't want that to happen. We don't want to have them too little energy, because then the electron clouds will repel each other. They need to just have enough energy, more than the activation energy, but not too much energy. The second thing that's really important from collision theory is they must orientate themselves. They must have the correct orientation. So if the unpaired electron is sitting, for example, on one molecule over here, or that's the bonding position, and the other one is on the back of it, and they bump into each other, no reaction. So they must have correct orientation. Correct spatial, that means just in space, spatial orientation. Okay, so these are critical ideas in terms of collision theory. We need to make sure that they have that they're ready for bonding as well, so that they're likely to form product molecules. But those are two big conditions, and we've gone through that first question. Now let's go on to the next one. It tells us that we have a particular reaction, and the reaction is given here. I just want to change the color of the pen. We told the reaction between nitrogen dioxide and carbon monoxide is represented by the equation below. There's your nitrogen dioxide, there's your carbon monoxide, and we're getting nitrogen 2 oxide and carbon dioxide. Remember the information here, delta H is minus 226 kilojoules. That's telling you about whether it's endothermic or exothermic. We need to just go over those terms. Exothermic means that more energy is given out in the reaction, and delta H is negative. Endothermic, delta H will be positive, and it's saying more energy is taken in, less is given out. Okay, so revise those terms and make sure you've got them sorted out. We'll come to them again. It tells us that the activation energy is 132 kilojoules. Now, it says sketch a potential energy graph against the reaction coordinate for this reaction. Label the reactions and indicate the delta H and the activation energy on the graph. So let's go to it over here. I'm going to pick a system of axes, and we do that, and let's draw in. This is bookwork, and you should really know this stuff quite well. Revise it, get your notes sorted out so that you've got it perfectly sorted out here. Now, remember what we've said. We've interpreted the data. We've said over here, this is a negative, so it's exothermic. It's telling us that the energy, potential energy of the products is less at least than the energy of the reactants. So there's the products. The products is down here. And the reactants are up here. So this is potential energy, and these are the reactants. And the products are down there. So now, what else do we know is going to happen in terms of the reaction coordinate? So we just say reaction coordinate, because it told us to label the axes, and it's potential energy. You could write it in words in kilojoules, and we want to be able to show it on the graph, so we need to make sure we label it carefully and label it accurately. So what's the next thing? We've got 132 as the activation energy and minus 226 as the delta H. So delta H, enthalpy, the energy of reaction, heat of reaction, the amount of the difference between the product and the reactants. We've got them in the right position. So what we're going to say is the difference between these two. This is an exothermic reaction, and the difference between those two is your delta H value. So this value is going to be minus 226 kilojoules. And I'll put a minus in there so that we know it's exothermic. Remember, you need to label that, and then we need to complete the drawing. So what happens? The next part. We know we need to put some energy in to get the reaction going, and energy is given out. Now, let me just neaten that drawing up there a little bit. fill that in and get it in a straight line, and we've got it like that. So where's the activation energy now? Remember, activation energy is the energy that you start with until it forms a in-between situation up here. This is called your intermediate point. That's the most energy that's taken in. It's known as the coordinate. It's the reaction, it's a complex. In other words, what's happened here is the two molecules have joined together, and the new bonds and the old bonds haven't quite broken. It's an intermediate stage. It's the activation complex that is formed at that point. Now, when you get this complex molecule of these two things kind of stuck together, they haven't quite bonded yet, and they haven't quite broken all the existing bonds. They then can either break apart to form reactant molecules, or form new bonds to make product molecules. So we call this the activation complex. Activation complex, and that's your activation energy. Now, why is activation energy important? Well, here's the thing. Ty, I don't know if you know that, I mean, you've got some books sitting on your desk at the moment, and those are mainly made out of carbon. Okay, and there's oxygen in the room. So guys, we know that oxygen and carbon, paper burns. So why aren't the books combusting at the moment?
I'm pretty sure it's because there's not enough volatile energy to cause them to.
Okay, correct. There's not enough activation energy. We'd need a little spark. And hopefully we don't have too many sparks flying around in the studio today. But if we had a little spark provided by a lighter or a match, that would give enough energy to get some molecules excited enough to start reacting with each other. So the carbon molecules in the paper would react with the oxygen molecules in the air. And the next thing, there'd be an exothermic reaction, and we would see flame. Flame is an emission of light and heat. And so that's why we say this is an exothermic reaction. In this particular case, you might not see flame and heat, but you'd be able to measure a change in temperature. Okay, so I think that we've more or less answered the question. Once you've put things in, make sure that you reread your question. So after you've gone through the question and you think you've finished, just read through and make sure you've got everything sorted. So it said sketch a potential energy. Yeah, potential energy I've written as EP versus reaction coordinate. I've labeled that for this reaction. Label the axes and indicate the following on your graph: delta H and EA. So I've shown the delta H just to make sure that people are perfectly happy with me. I'm going to put in another line just to show where the EA, the delta H comes to. So it's the difference between the product and the reactant. So I could move this arrow over here because it's from that line to that line, and my line was just a little bit short, so let me make sure that you've got that. You need to work accurately. It's between these 2 points here. Make sure that you've got that very clearly put in, and make sure that we've got it as minus 226 kilojoules. Ty, any questions on the page at the moment?
Not as of yet. Right now, I'm just pretty much waiting for the page to reload.
Okay,
so
that's fine. Let's go on to the next part of this question. Well, we have done the rates of reaction question. I think we could go to a short break if there's nobody asking. One further thing, guys, just before we do go to that break, what are the type of questions that are being asked in more recent exam papers on rates of reaction? And the thing that you need to remember is, apart from these, look there, I missed the question. I knew there was another one. Here we go. Use a broken line on your graph to show the effect of a catalyst. And that was just the point that I was coming to. So the effect of a catalyst on the potential energy as the reaction proceeds. The point I was going to make is, guys, you've got to know the 5 or the 4 factors that affect a rate of reaction. It's the concentration of reactants, it's the temperature, it's the surface area, and it's the effect of a catalyst. So let's deal with the effect of the catalyst. What is a catalyst, and what does a catalyst do? A catalyst is a substance, it's a chemical substance that we introduce into a reaction and it takes part in the reaction, but it isn't used up. So we start with a certain number of moles or mass of catalytic substance. At the end of the reaction, we would have the same mass, the same molecules, the same number of moles. It's not used up. It can be changed in the reaction. It helps to make the reaction happen faster. It helps speed up the rate of reaction without being changed itself, without being used up itself. Okay? So it effectively lowers the activation energy. So instead of having an activation energy of 132 here, if I were to put a catalytic reaction in this example, I'm going to use that color, then the catalyst would go up to there, it would end in the same place, and this line here is with a catalyst. So you can see that it says draw broken line. I've just used a different color. It's just easier to do it smoothly on the board. Hope you can see, follow the instruction. That should be a dotted line to indicate that that's the catalytic. Notice that the energy, the activation energy, this is the activation energy now, and it's going to be less than the original 132. Okay, remember that when they're asking these questions now, they often ask about investigative questions. They set it up and say to you, describe what is an investigation, what's the investigative question, what's the hypothesis, what variables would you control, and ask questions like that. That's the way they've been tending to examine this section in the last couple of years. Okay, Ty, over to you.
All right, so mindsetters, I'm seeing and I'm loving what you guys are doing on the page. Keep posting. But guys, we need questions. Make sure you post questions. And guys, don't forget to call in on 0861 058 262. Make sure, because you could stand a chance to get one of these books, this pack sent to you. But guys, again, do not go anywhere. Make sure you stay tuned, and we'll see you after this break.